Picture this. You're driving to a crucial meeting.
Oh, we've all been there.
Right. Like, it's the kind of meeting that could define your entire career, and you are running exactly 4 minutes late.
That is the worst feeling.
It really is. So naturally, you pull up your favorite navigation app, you plug in the destination, and you hit optimize for shortest time.
Because you trust the app. You just do what it says.
Exactly. You follow the little glowing blue line on the screen. But 10 minutes later, instead of pulling up to a sleek office building, you find yourself creeping down this terrifying, unpaved, garbage-strewn back alley.
Yeah, the classic GPS nightmare.
Right. Your car's suspension is screaming, there are dumpsters blocking half the path, and you're pretty sure you just drove over a discarded mattress.
And you're just sitting there wondering, how did I get here?
Yes. Why? Because that specific route, mathematically speaking, saved you exactly 12 seconds compared to the main road.
Wow. 12 seconds.
12 seconds. The app didn't fail. I mean, it didn't glitch. It did exactly, precisely, flawlessly what you asked it to do. Minimize the time at all costs.
Regardless of the physical chaos it drags you through to achieve that number.
Exactly. It's terrifying, really.
It is the ultimate monkey's paw scenario. You got your wish, down to the decimal point, but you realize too late that you wished for the wrong thing entirely.
Yeah, because the system gave you the metric, but completely ignored the context.
Right. It ignored what a human being actually considers a quote-unquote good drive.
And that realization that the algorithms we trust are essentially blind, obedient genies, that's the foundation of what we're looking at today. We are taking a deep dive into a really fascinating research paper.
It's a fantastic paper.
It's from the Backtest Without Illusions series by an author who goes by Sunat. And the paper is titled Objective Function Design. The metric you optimize secretly picks your strategy.
It is a phenomenal title because it captures a blind spot that exists across almost every data-driven industry right now.
It really does. I mean, we spend so much time building complex AI and these intricate machine learning models.
And massive parameter search.
Exactly. But we rarely interrogate the single scalar number, the objective function that we actually use to grade their homework.
Which is wild when you think about it.
Yes. So today's journey is going to explore how those algorithms and hyperparameter tuners that we trust to find the quote-unquote best solutions don't actually know what good means.
They have no concept of safe or reliable or logical.
None. They only know the math we feed them. Okay, let's unpack this. Because the overarching principle here is something that spans far beyond just algorithmic trading.
Right. It's a universal law of complex systems. You might know it as Goodhart's law.
Oh, yeah. Named after the economist Charles Goodhart back in, 1975?
Yeah, exactly, 1975. The famous rule of unintended consequences. Any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes.
Though most people know the tighter paraphrase, right?
Yeah, the Marilyn Strathern version. When a measure becomes a target, it ceases to be a good measure.
It ceases to be a good measure. Such a powerful quote. And the author of our source points out that a parameter search is basically the purest, most concentrated instance of Goodhart's law in action.
It absolutely is.
Yeah.
Let's say you tell the algorithm to maximize a Sharpe ratio.
Which, for those who don't know, measures risk-adjusted return.
Right. So that Sharpe ratio is your measure, and the search algorithm itself, that is the pressure.
And when we say pressure here, we aren't talking about a manager casually asking their team to hit a quarterly goal.
No. We are talking about silicon. We're talking about millions of calculations per second.
Right. Relentless.
It represents thousands, maybe millions of iterative attempts to push that single measure as high as the mathematics will physically allow.
It's like, imagine a topographical map of possibilities, right?
Yeah, and the algorithm acts like a blind hiker. Its only instruction is to walk uphill.
Walk uphill no matter what. It'll climb any spike, no matter how precarious, just to get a higher altitude reading.
Exactly. And the hiker doesn't care if that spike is a fragile needle of rock that's just going to instantly collapse under real-world weight.
It doesn't care what you meant by find the highest ground.
It doesn't know that when you typed maximize Sharpe ratio, what your human brain actually meant was find me a robust strategy I can trust with real money.
Yeah, without bankrupting my clients.
Right. And this is exactly what the AI safety literature refers to as reward hacking.
Reward hacking. I love that term.
It's so descriptive.
Yeah.
You give an artificial intelligence agent a proxy metric, a stand-in for your actual goal, and the agent exploits every microscopic gap between that proxy metric and your true human intention.
Like the video game AI that kills itself at the end of level 1 so it never loses points in level 2.
That is the perfect example of reward hacking.
Yeah.
Your search algorithm is that agent. The metric is the proxy.
And the gap between them is where all the danger lives.
All of it.
So to truly understand this reward hacking, the author makes a brilliant structural point. We can't just look at messy real-world data to study this.
No, real-world data is way too contaminated.
Yeah, if you design a trading strategy on historical S&P 500 data and it completely bombs when you take it live, why did it bomb?
Was your objective function flawed? Or did the macroeconomic regime shift?
Right. Was there a global pandemic? Did the Fed change interest rates?
You can never untangle the failure of the metric from the sheer chaos of reality.
It's impossible. So to really prove this theorem, the researchers had to play God.
They had to build a universe where they knew the exact absolute truth, free from any real-world contamination.
So they built a synthetic market.
A completely artificial, mathematically closed universe.
And in this universe, they can introduce a known edge, like a real mathematically guaranteed predictive signal, right?
Exactly. And then they just sit back and watch how different objective functions try to hunt for it.
Okay, let's spend some time on the physics of this artificial universe, because how they built this sandbox is crucial to understanding the trap later. What are the rules here?
They kept it elegant, but rigorously challenging. Let's think of it as a time series. Okay, in this synthetic market, each time period, a predictive signal arrives. The paper calls this sub-T. It's a standard normal signal.
Meaning the signal values are distributed along a classic bell curve, centered at 0.
Right. And this signal is immediately followed by a market return, R sub T. Now, the signal partially predicts that return.
So if the signal is positive, the market is more likely to go up. If it's negative, it's more likely to go down.
Essentially, yes. But here is the brilliant design choice that really forces the optimizer to make hard decisions.
Oh, the band. This part is so cool.
The edge, the predictive power of this signal, is real, but it is bounded. It only exists inside a moderate signal band.
Specifically, the relationship only holds true when the absolute value of the signal is less than or equal to 1.
Yes. So if the signal is a 0.5, it has predictive power. If it's a negative 0.8, it has predictive power.
But if the signal is a 2.5 or a negative 3,
anything outside of that band carries absolutely zero predictive information.
it is pure, unadulterated noise.
Pure noise, mathematically disconnected from the return that follows it.
Wait, I want to make sure everyone grasping this, because normally we assume that a louder alarm means a bigger fire, right?
Actually, yeah.
But here, if the signal is really big, really extreme, it actually means nothing.
Nothing at all. It's just static.
Yeah.
And that was a very deliberate, highly intelligent choice by the researchers.
Because amateur algorithms just look for momentum.
Exactly. They wait for a massive spike and just jump on the bandwagon. But because extreme signals carry no predictive information here, a successful strategy has to learn nuance.
It has to learn to trade the middle of the distribution and explicitly ignore the screaming extremes.
Right. It has to know when to engage and, just as importantly, when to sit on its hands.
That is such a phenomenal setup. You're forcing the algorithm to exercise restraint. But since this is a closed universe, how do we know what the absolute perfect strategy is?
Well, because the researchers wrote the underlying equations, they can mathematically derive the absolute theoretical maximum profit.
They don't have to guess or backtest to find it.
No, they can calculate the literal ceiling of reality. The strategy they're testing is a one-parameter family based on a single threshold.
Which they call theta, so it's just one knob to turn.
One knob. You turn the knob to set your threshold. The rule is you trade in the direction of the signal whenever its magnitude is below your chosen theta.
And if the signal is larger than theta, you do nothing. You just sit flat.
Exactly. Turn the knob all the way down, you almost never trade. Turn it all the way up, you trade every single bar.
Including all that toxic, useless noise at the extreme tails.
Right, so the algorithm's entire job is just to find the perfect setting for that one knob.
The Goldilocks zone. What is it in this universe?
The absolute mathematical optimum, the ground truth, sits at a threshold of approximately 1.04.
1.04.
At that threshold, you sit exactly at the edge of the real signal band without stepping over into the noise. You stay in the market about 70% of the time.
And what's the payout?
Mathematically, it yields an expected out-of-sample annualized Sharpe ratio of exactly 1.77.
1.77. That is the hard ceiling of this universe.
That is the number every objective function is supposedly trying to find.
Because this is a synthetic universe, any objective function that picks a strategy deviating from this 1.77 ceiling isn't failing because the market is hard to predict.
No, it's an unarguable failure of the objective function itself. It
Yeah.
means the metric lied to the search algorithm.
Okay, I am tracking with you completely. But if I put myself in the shoes of a skeptical data scientist listening right now, I have to push back a little on this methodology.
Sure, let's hear it.
If the researchers built the market, isn't it inherently too perfect? Aren't they rigging the game to prove their own point?
It's a common critique.
I mean, it feels a bit like testing a new type of umbrella in your shower stall instead of taking it out into a thunderstorm. It's sterile.
It is a totally valid skepticism. But we need to flip that analogy. Think of it less like a shower stall and more like a highly calibrated aerospace wind tunnel.
Ooh, a wind tunnel. I
Um,
like that. Expand on that.
If you're an aerospace engineer designing a radically new airplane wing, which represents our objective function here, you cannot test its fundamental aerodynamics by flying it into a Category 5 hurricane.
Right, because a hurricane is purely chaotic.
Exactly. If the wing snaps off in a hurricane, what did you actually learn? Did your math fail? Did flying debris strike the wing?
Did the pilot make an error? Did a microburst hit it?
You learn nothing about the structural math of the wing because there are just too many confounding variables.
So you need a controlled environment where you know exactly how fast the wind is blowing.
The exact air pressure, the exact humidity. Only in the wind tunnel can you isolate the mechanism of failure.
So the synthetic market is our statistical wind tunnel.
Precisely. And to address the concern about it being too sterile, the researchers actually piped in a specific type of turbulence to mimic the harshest realities of real-world finance.
Fat-tailed noise.
Yes. The noise in the market returns. The chaotic variance that cannot be predicted by the signal wasn't modeled using a polite normal bell curve.
They used a student distribution with 4 degrees of freedom.
They did.
Okay, if you're listening on your commute right now and your eyes are glazing over at the phrase student distribution with 4 degrees of freedom, stay with us.
It's actually a really crucial detail.
It is critical to how the trap snaps shut later. What does that mean mechanically?
Mechanically, it means we are breaking the assumption that data behaves nicely. In a classic bell curve, extreme events are incredibly rare.
A 3 standard deviation event might happen a couple of times a decade.
Right. And a 5 standard deviation event shouldn't happen in the lifetime of the universe. But in real financial markets, those massive catastrophic spikes happen all the time.
The 1987 Black Monday crash, the 2008 financial crisis, the COVID drop in 2020.
Those are fat tails. The tails of the bell curve are literally thicker because more data points fall into those extreme edges.
So by using a distribution with just 4 degrees of freedom, the researchers inject a massive amount of excess kurtosis.
They ensure that extreme, unpredictable, violent price swings happen frequently in this synthetic universe.
The market might be artificial, but the turbulence is designed to be just as dangerous and deceptive as the real S&P 500.
Exactly. But the beauty of the wind tunnel is that despite this violent noise, we know the absolute true underlying optimum is a Sharpe of 1.77.
And now we can unleash a standard metric into this environment and watch it spectacularly fail.
Oh, it gets torn to pieces.
The paper walks us through this absolute horror story they call Seed 6.
Yeah, Seed 6 out of 600 independent market seeds they ran.
Which are like 600 parallel universes of this identical market setup. Same rules, different random noise. And in this specific universe, Seed 6, they told the search algorithm to maximize a metric called the per-trade Sharpe ratio.
Also known in the industry as the active Sharpe.
What exactly does that measure?
It is the Sharpe ratio computed only on the bars where the strategy was actually in the market, holding a position. It completely ignores any time the strategy spent sitting in cash.
Which, if we are being honest, sounds incredibly logical. I can completely see why a human would design that.
It feels very intuitive.
You think, when it actually decides to trade, how good are those specific decisions? You'd think isolating the active bars separates pure skill from just sitting around doing nothing.
So the algorithm accepts the mission. It looks at 80 different candidate thresholds for our one knob.
And it comes back down the mountain and crowns a winner. It says, behold, the greatest strategy. And the stats on this winning strategy are mind-bending.
Unbelievable
It
stats.
picked a threshold setting of 0.0005. Its market exposure was just 0.4%, and its in-sample annualized Sharpe ratio was 21.09.
21.09. A Sharpe ratio like that exists only in fairy tales and Bernie Madoff's pitch decks.
Seriously. I mean, for context, the greatest quantitative hedge funds in the world, places like Renaissance Technologies, are thrilled to maintain a Sharpe of 2 or 3 over a long horizon.
A Sharpe of 21 means the equity curve looks like a straight line drawn with a ruler aiming directly at the moon.
But then you look under the hood, how many trades did it actually make to generate that 21.09 Sharpe? Out of 2,000 possible time periods, it made 8 trades.
Just
8. It sat completely flat, doing absolutely nothing for 99.6% of the time, popped its head out exactly 8 times, got lucky on those 8 specific bars, and claimed it was the undisputed mathematical champion.
And, of course, the moment of truth.
Yeah.
When they tested this champion on fresh-out-of-sample data, that massive 21.09 Sharpe completely collapsed.
It plummeted to an abysmal 0.13.
A total mirage. Functionally useless.
It's like a baseball player who gets called up from the minor leagues, steps up to the plate on opening day, takes exactly one swing, hits a home run, and immediately walks off the field and retires.
And then demands to be in the Hall of Fame.
Yes, because they are mathematically infinitely better than Babe Ruth. Their batting average is 1.000.
Technically true based on the metric.
But practically, it's a complete joke. How could any data scientist see a Sharpe of 21 and not immediately realize it's a trap?
This is where we have to dive deep into the mechanics of the search algorithm itself. Because the algorithm isn't stupid, it's mathematically flawless.
It's just blind.
Exactly. To understand why an automated search algorithm hurls itself into this trap every single time, we have to look at the statistical reality of small sample sizes.
The paper brings in Andrew Lowe's 2002 standard error formula for Sharpe ratios, right?
Yes, to explain the physics of this mirage.
Okay, break down the mechanics of this formula for me. Don't just give me the result. Explain how it works.
Let's visualize the formula. Andrew Lowe proved that the standard error of a Sharpe ratio, basically how much you expect it to bounce around just by random chance, is fundamentally governed by the number of observations.
Which we call T.
Right, T. Let's assume perfectly independent returns, beautifully normal distributions, no fat tails. In that perfect world, the standard error shrinks proportionally to the square root of T.
The square root of the number of trades.
Exactly. Because T is in the denominator, the larger your sample size, the smaller your error. If you have 10,000 trades, the square root is 100. Your error shrinks dramatically.
Metric stabilizes.
But what happens when T is tiny?
The denominator shrinks, which means the error explodes.
Right. Let's apply Lowe's formula directly to our seed 6 winner. It has an annualized per trade Sharpe of 21.09.
Okay.
If you de-annualize that to find the raw score per observation, it's roughly 1.33 per trade, computed on a sample size where T equals exactly 8.
Just 8 observations. So the square root of 8 is what, around 2.8?
Exactly. It's a tiny denominator. When you plug that into Lowe's formula, the standard error per observation is massive, about 0.49.
And when you annualize that standard error...
You get an error band of roughly plus or minus 7.7.
Wait, I need to visualize this. The point estimate, the number the algorithm is waving in the air, is 21, but the 1 sigma error bar is plus or minus 7.7.
Yeah, and that's just a 68% confidence interval.
That's not a margin of error, that's a canyon. The real Sharpe could be 13, it could be 28, it's just floating in the void.
It carries essentially zero mathematical information. You have no idea what the true skill of the strategy is. And remember, that calculation is the charitable version.
Because that assumes standard normal returns.
Right. As the paper points out, citing Merton's extension of Lowe's formula, when you introduce the fat-tailed noise that is actually present in this synthetic wind tunnel, the physics get even worse.
Because of the kurtosis, the extreme events, how does that alter the error?
Fat tails mean that the variance itself has high variance. The skew and kurtosis act as multipliers on the standard error. They inflate that plus or minus 7.7 even further.
So a Sharpe ratio built on 8 fat-tailed trades is statistically meaningless.
It is less trustworthy than its own point value in every direction at once.
So if the error is so massive, why does the algorithm pick it? If it's a blurry mess, why does the optimizer view it as the peak of the mountain?
Because of the fundamental nature of optimization. Imagine a landscape with 80 hills representing the 80 thresholds.
Okay.
Most of the hills represent robust, high trade count strategies. Because they have thousands of trades, their standard errors are tiny. Their hills are smooth, stable, and max out around a Sharpe of 1.77.
But then there are the low trade count strategies.
Exactly. The ones that only trade 8 times or 15 times have massive standard errors. Visually, these aren't hills. They are jagged, volatile spikes.
Ah, I see.
The true value of a low trade strategy might be 0. But because its error band is plus or minus 7.7, just by random luck, in one parallel universe, the noise will stack positively.
That spike will randomly register at 21.
And the optimizer is blind. It doesn't see standard errors. It only sees point estimates. It sweeps its hand across the landscape, feels the tip of that jagged lucky spike at 21, and declares victory.
The metric isn't actually finding a brilliant strategy. It is actively hunting for the wildest statistical anomalies.
It is selecting for its own unreliability.
That is the core trap. The per-trade metric fundamentally rewards trading as rarely as possible because fewer bars make it statistically easier to capture a few lucky draws of noise.
If you were in the market for 1,500 bars, you can't fake it. The law of large numbers catches up with you.
The noise cancels itself out, but the per-trade metric never asks, hey, were you actually in the market long enough to prove this isn't a fluke?
The metric is maximized by driving the observation count toward the absolute minimum.
Okay, this is blowing my mind, but I have to play devil's advocate here. Seed 6 is just one universe out of 600. It's a spectacular horror story, sure.
The authors even explicitly admit they cherry-picked it to show the most dramatic collapse.
Right. So as a listener, I have to ask, is this just a freak accident? A 1 in a million edge case? Or is this a systemic disease with the per-trade metric?
It is an entirely systemic disease. The paper expands the scope to the full 600-seed Monte Carlo simulation.
600 independent draws of the market universe.
600 chances for the per-trade Sharpe to find the right answer. And the aggregate results are devastating. The per-trade Sharpe selects a degenerate winner 57% of the time.
Let's define degenerate carefully in this context, because that's a loaded term.
In the paper's taxonomy, a degenerate winner fails in one of 2 catastrophic ways. Either it sits in the market less than 5% of the time, meaning it is functionally just a lottery ticket, or it posts a non-positive out-of-sample Sharpe ratio, meaning its true edge is literally 0 or negative.
57% of the time. Functioning perfectly as designed, your multi-million-dollar quant infrastructure hands you complete, unadulterated garbage more than half the time.
And it gets worse when you look at the averages. Across all 600 seeds, the typical degenerate pick has an average in-sample per trade Sharpe of 4.58.
Okay, that's not the astronomical 21 we saw in the Freep show, but a 4.58 is incredibly dangerous.
Very seductive.
If a junior quant brings a backtest with a 4.5 Sharpe to a portfolio manager, they are getting a bonus, and that strategy is going live.
Seductive and entirely false, because when that 4.58 is exposed to fresh data, it collapses to an average of 0.70.
A massive drop, a complete failure to generalize. But I want to talk about how the researchers diagnosed this failure, because this is where the scientific rigor of the paper really shines.
The honesty notes section.
Yes. Because it would be so easy to point the finger at the fat tails. You look at a 57% degeneracy rate and think, well, obviously, extreme events happen often in this market, so of course a short window strategy gets lucky.
It feels like the logical culprit. The hurricane blew the wing off, the environment was too hostile.
But the researchers refused to just assume that.
They ran a control experiment to test that exact hypothesis. They generated 300 entirely new market seeds, but this time they removed the fat tails.
They used standard, polite Gaussian noise.
No massive spikes, no Black Mondays, just a serene, gentle wind tunnel.
Did the per-trade metric suddenly wake up and start working?
It failed identically. Under gentle Gaussian noise, the degeneracy rate was 55.7%.
Compared to 57% with fat tails.
Exactly. The out-of-sample Sharpe under Gaussian noise was 0.71. With fat tails, it was 0.70. The results are practically indistinguishable.
That is incredible. So the heavy tails in the market have absolutely nothing to do with why this metric fails.
The environment is irrelevant. The researchers emphasize that this proves the trap is a pure, structural, small sample plus selection artifact.
It doesn't matter what the noise distribution looks like.
If you tell an optimizer to take the maximum Sharpe across dozens of options, and it can compute that Sharpe on just a handful of observations, some random corner of the data will always look spectacular by pure luck.
The algorithm will always find the corner where the noise impersonates signal. Here's where it gets really interesting. Because if the per-trade Sharpe is such a disaster, the intuitive fix is right in front of us.
What are you thinking?
What if we just strip the complexity away? What if we tell the algorithm to maximize total cumulative profit? raw P&L.
Ah.
Surely the algorithm cannot hide in a bunker with 8 trades if its explicit instruction is to make the biggest possible pile of money by the end of the timeline.
Your intuition is spot on. If you optimize for raw P&L, the algorithm realizes very quickly that sitting in a bunker earns $0.
And the degeneracy rate drops.
It drops to exactly 0%. It never once picks a strategy that barely trades.
Problem solved. We can all go home. The per-trade Sharpe is a trap. Raw P&L is the savior.
Not quite. If the per-trade Sharpe fails by hiding in a bunker, raw P&L fails by running blindfolded into highway traffic.
Oh no, what does it do? Why is it running into traffic?
Because it has the exact opposite structural bias. Raw P&L overexposes. Let's go back to our established ground truth. The perfect strategy has an exposure of about 70%, yielding an out-of-sample Sharpe of 1.77.
Right, the 1.04 threshold.
When you unleash an optimizer and tell it to maximize raw P&L, it reaches a mean market exposure of 85.9%.
It pushes the threshold knob past the optimal boundary.
Far past it. In that same Seed 6 universe, raw P&L picked a threshold of 1.84.
But wait, explain the mechanism there. We established that any signal above 1.04 is mathematically pure noise. It carries 0 predictive weight. Why on earth is the optimizer choosing to trade at 1.84?
Because raw P&L only cares about cumulative summation. Even if a trade is 99% noise, if there is a tiny...
It has no concept of risk-adjusted return.
None. It drags massive amounts of out-of-band noise into the portfolio just to be in the market more often.
It will happily suffer massive volatility and drawdowns if it means ending the simulation with $2 extra.
The result is an aggregate out-of-sample Sharpe of 1.61.
Which is noticeably structurally worse than the true optimum of 1.77.
It doesn't blow up spectacularly like the per-trade Sharpe, but it consistently drifts away from the real optimum in the opposite direction.
And this contrast proves the central thesis of the entire paper. The metric you select is the strategy you get.
You didn't just tell the algorithm how to score the test. You accidentally gave it personality.
Per-trade Sharpe is a coward. Raw P&L is a reckless gambler.
Exactly.
So we are caught between a rock and a hard place. How do we fix this? The paper focuses on rescuing the per-trade Sharpe with 2 mathematical cures. What is cure number 1?
Cure 1 is called an exposure floor. The researchers denote this as E-min equals 0.20. It's a blunt force instrument.
You just inject a rigid rule?
Yes, you reject outright any strategy that is not in the market at least 20% of the time. If a candidate barely trades, its score is automatically set to negative infinity.
Honestly, I like that. It's clean. It's like a bouncer at a club. You don't have at least a 20% attendance record. You're not getting in. Why isn't that enough?
Because mathematical discontinuities create blind spots. A hard cutoff is fundamentally inelegant, and optimizers hate it. Think about the edge case.
What happens if a strategy discovers a genuinely brilliant signal, but it only triggers 19.9% of the time?
The bouncer throws it out. It gets a score of negative infinity, even if its true out-of-sample Sharpe is incredible.
And conversely, a garbage strategy that trades 20.1% of the time gets let into the club.
The algorithm will actually warp its behavior to just barely clear the 20% hurdle and then resume its reward hacking.
So the blunt force approach is flawed. We need something that scales smoothly. What is cure number 2?
Cure 2 is much more sophisticated. It is a trade count shrinkage, which they call config. In their baseline test, they set the constant k equal to 40. This applies a continuous mathematical penalty curve. You take the raw per trade Sharpe ratio and you multiply it by a fraction, n divided by n plus k.
Where n is the actual number of trades.
Exactly.
Okay, let me do the math on this to see how it feels. If n is the number of trades and k is this constant of 40, let's take our disaster strategy from Seed 6. It made 8 trades.
Right.
So the multiplier is 8 divided by 8 plus 40. So 8 divided by 48, that's 1/6.
Precisely. The raw score is crushed. Even if the raw Sharpe is an astronomical 21, multiplying it by 1/6 severely diminishes its appeal.
The score drops to, what, 3.5?
Yes. Suddenly, the 21-point spike is chopped down to size.
But what happens to a good strategy? A robust one?
As the number of trades grows massive, say, a strategy with 1,000 trades, the fraction becomes 1,000 divided by 1,040.
That evaluates to 0.96.
It gets very close to 1, meaning the robust strategy keeps almost all of its raw score.
That makes profound sense. This reminds me a lot of building a credit score.
Oh, that's a good analogy.
You don't get an 800 credit score just because you borrowed $5 from a friend one time and paid it back the next day.
No, the bank doesn't care.
Right. You technically have a 100% repayment rate, but they look at your n equals 1 and apply a massive shrinkage to their trust. You need a volume of history to prove it's not a fluke.
The bank is applying Bayesian skepticism, and the mathematics of this shrinkage are directly tied to how quantitative finance handles track records. This specific formulation is a Bayesian precision-weighted shrinkage.
Let's break down that jargon. What does that mean in plain English?
Bayesian thinking always starts with a prior, a baseline assumption before you look at the data. In this case, the prior is extreme skepticism. The math assumes your strategy has zero edge.
That is the baseline.
As you generate profitable trades, you provide evidence to pull the score away from zero. But the precision weighting part means that small amounts of evidence don't have enough gravitational pull to move the needle much.
It requires a massive volume of evidence to overcome the skeptical prior. The paper connects this to Bailey and Lopez de Prado's minimum track record length, right? Min-TRL.
Yes. Min-TRL inverts the standard question. Normally we ask, what is the Sharpe ratio? Min-TRL asks, given the variance, how many observations do I physically need before I am mathematically allowed to believe a Sharpe ratio of this size?
It turns the conceptual requirement into an explicit number of trades, and there's another concept they connect it to.
Van Tharp's system quality number, or SQN. It also forces a per-trade metric to scale with trade count, but it uses the square root of the number of trades as a direct multiplier.
The functional form is different, but the philosophical intent is identical. A good objective function must enforce a minimum track record from the inside.
From the inside, exactly. You aren't handing a metric to a human committee to say, only 8 trades? Toss it.
You're pricing the unreliability directly into the number itself. The optimizer self-regulates. But I have to ask, how do we know 40 is the magic number for K, or 20% for the floor?
If you just guess 40, you are absolutely curve-fitting.
Are we just cheating?
The authors address this head-on. They state explicitly that the specific numbers are entirely scale-dependent. They're tuned specifically to this synthetic market.
So if I try to use K equals 40 on a high-frequency crypto algorithm, it's going to fail?
Spectacularly. A high-frequency algo might make 10,000 trades a day. A K of 40 would do nothing. Conversely, if you trade a macroeconomic strategy that fires once a year, a K of 40 crushes your score to 0 forever.
So if the exact numbers don't generalize, what's the point of the paper showing them to us?
Because what matters isn't the specific coordinates. What matters is the shape of the sweep surface.
The sweep surface.
They ran hundreds of combinations of the floor and shrinkage across 200 market seeds. When plotted on a 3D surface, moving in either direction, increasing the floor or the shrinkage, produced a monotone lift in out-of-sample performance.
And drove the degeneracy rate towards 0.
The surface reliably and beautifully plateaus exactly at the mathematical truth of 1.77. You find your own coordinates for your own market by running a similar sweep, but the structural mechanism works universally.
So when they combine these two cures, they create the robust objective, and the results are genuinely impressive. Out-of-sample Sharpe hits 1.70, incredibly close to the 1.77 ceiling.
And the degeneracy rate drops from 57% to a microscopic 0.17%.
It seems like a massive triumph for complex mathematics.
They successfully engineered a shield against Goodhart's law.
But I read this paper. I know there is a plot twist coming. When I was reading this section, I was convinced they had solved it with this conflict shrinkage.
The math is beautiful.
It is, but then I turned the page to their final comparison table, and I actually laughed out loud at what beat it.
It is a massive, humbling plot twist.
Reveal it for us.
This beautifully complex, heavily engineered, robust objective, which hits 1.70, is actually weakly dominated by the simplest, oldest metric of them all.
Plain, old, unmodified, full-time line Sharpe.
Exactly. Full-time line Sharpe hits 1.71, slightly better than the robust objective, and it has a degeneracy rate of exactly 0%.
0. It never fails.
It requires no exposure floor, no trade count shrinkage, no tuning of arbitrary J constants. It just works flawlessly out of the box.
This is unbelievable to me. How does full-time line Sharpe work mechanically, and why does it effortlessly defeat the per-trade trap? You called it denominator management earlier.
Let's use an analogy. Imagine a university grading system.
Okay, I'm back in college. Let's go.
You have a student who wants to graduate with a 4.0 GPA. The per-trade metric is like allowing that student to calculate their final GPA using only the classes they actually showed up for.
Oh, wow. So if I enroll in 40 classes over 4 years, but I skip 37 of them entirely and only show up to 3 classes where I know I can get an A.
Under the per-trade metric, you have a 4.0 GPA, you are the valedictorian,
Yeah.
you hacked the reward system by minimizing your sample size and self-selecting the victorious moments.
That is exactly what Seed 6 did. And what is full-time line Sharpe in this analogy?
Full-time line Sharpe is the university registrar stepping in and saying, no, your GPA is calculated based on the total number of credit hours you enrolled in, period.
So if you skip 37 classes, it automatically enters a 0 for every single one of those classes.
Exactly. All of those zeros go into the numerator of your GPA calculation, dragging the sum total down, while the denominator remains fixed at 40 classes.
My GPA plummets from a 4.0 to a 0.3.
Think about what the full-time line Sharpe measures in a financial context. Unlike the per-trade Sharpe, it forces every single moment of the market's existence into its calculation.
Every flat bar, every moment of idleness, every second it's hiding in a bunker is recorded as a return of exactly 0.00%.
Yes, the denominator might be small because zeros have no variance, but the numerator is crushed to almost nothing.
You physically cannot game a full timeline metric by trading rarely because every hour you sit flat, you're earning nothing, but the mathematical clock is still ticking against you.
Idleness is penalized perfectly and automatically.
That is profound. By giving the optimizer the power to choose which bars to measure, you give it the power to lie to you.
A self-selected window is an open invitation to reward hacking. The exposure floor and the shrinkage are mathematically brilliant, but in the end, they're just clumsy retrofits.
They're just simulating the natural exposure awareness that the full timeline metric already has.
If you are free to choose the window, choose the whole timeline and skip the retrofit entirely.
I remember another analogy for this. It's like the astronaut pen versus the pencil.
Oh, the classic space race myth.
Right. The story goes that NASA spent millions inventing a pressurized zero-gravity pen for astronauts, while the Soviets just handed their cosmonauts a 99-cent pencil.
Which is historically inaccurate but conceptually perfect for this.
Exactly. The retrofitted robust metric is the $1,000,000 zero-gravity pen. It works, it's brilliant engineering, but full-time line Sharpe is the 99-cent pencil. It was sitting on your desk the whole time.
Just use the pencil.
So, crystallize this for us. What is the ultimate hierarchy of objective design? If I am setting up a massive parameter search tonight, what is my checklist?
The paper lays out a three-step hierarchy. Step 1, measure on the full timeline. This must be your absolute default.
Don't give the genie the loophole.
Precisely. Step 2, if you absolutely must use a conditional per-trade metric, maybe your capital is highly constrained, you must require an exposure floor. Put a hard limit that stops the search from retreating into a bunker.
And step 3.
Step 3 is to shrink by trade count. Discount any ratio by the n over n plus k formula to enforce a minimum track record from the inside. But remember, steps 2 and 3 are just patches. The true lesson is step 1.
So what does this all mean for you? Why should you care about this if you aren't writing algorithmic trading scripts? Because the core lesson transcends finance. The metric you choose is the strategy you get.
An optimizer is an obedient genie. It does not care about your business goals.
It only cares about maximizing the literal math you typed into the system. If you're running A/B tests for a marketing campaign and you optimize purely for click-through rate, the algorithm might just serve your ads to bots.
Because bots click the most. It doesn't care if they never buy the product. Your metric goes to the moon while your revenue goes to 0.
Or corporate KPIs. If you measure customer support purely by average handle time, the agents will start hanging up on people with complex problems.
The handle time drops to 40 seconds, but customer satisfaction is destroyed. It's the exact same trap.
Or even personal productivity. Measure success by hours spent at the desk, and you'll end up staring at a wall for 12 hours a day.
Perfectly optimizing your metric while accomplishing nothing. Which leaves us with a final, somewhat provocative thought.
Let's hear it.
The paper touches on AI reward hacking and Goodhart's law, and the implications are vast.
Right.
We just spent an hour proving that the moment a specific metric is known, an optimizer will ruthlessly game it.
We fixed it here by using a full timeline metric.
But what happens when the systems get infinitely more complex, like artificial general intelligence, or algorithmically curated social media feeds?
We told algorithms to maximize engagement.
And they found the statistical spike of outrage, because outrage keeps people on the platform. They maximize the metric and fractured society in the process. If every static metric we design will inevitably be gamed the moment it becomes the target, is the pursuit of the perfect objective function fundamentally a paradox?
Wow. If every wall we build just teaches the algorithm how to climb higher, can we ever build a wall it can't climb?
Perhaps the only truly robust objective function is one that is not static, one that unpredictably mutates its own definition, forcing the AI to actually learn the underlying fundamental skill rather than just memorizing the answers to the test.
It's like trying to hit a moving target, but the target is moving specifically to make sure you actually know how to shoot. That is a brilliant, slightly terrifying place to leave it.
Thank you so much for joining us on this deep dive into the hidden machinery of objective functions. The next time a navigation app tries to route you down a back alley to save 12 seconds, check the metric, because the secret hand on the wheel might be driving you straight off a cliff, all while telling you it's breaking a speed record. We'll see you next time.